Multivariable calculus, we're looking at lesson 13.2, and you can see our learning targets at the top. I can take derivatives of vector functions and I can integrate vector functions. First of all, let's just review continuity. And as we review continuity just for functions, a function is continuous at an x value of a if three criteria are met. And a lot of times we just write that with bullet point number 3. But you can see f is continuous at x equals a if f of a is defined. In other words, you wouldn't get an undefined value. You're not dividing by 0, getting a negative inside of a root, square root, something like that. Second of all, your limit as x approaches a of f of x exists. Your right hand and your left hand directions are in agreement. And then very importantly for number 3, and some textbooks just jump to this because it's an easier, more succinct way to write it, is you're saying that that limit as x approaches a of f of x equals f of a. And as soon as you write f of a, of course you are implying through that equality that f of a exists. Well, what's happening is for a vector function to be continuous at a particular t value, it's like jumping to bullet point number 3 right here. We're saying that the vector itself must exist. That's on the right-hand side. A vector of r of t sub 0, t naught, is defined. The limit, obviously, is defined and exists also, but they're equal to each other. So that's what continuity really means for a vector function. And this is setting the stage for derivatives. To take a derivative, you must be able to have continuity first. Of course, when you look at your I, J, K components here, your x, y, and z components of the vector, that implies that those functions must be continuous just as well. Well, wonderful news. Wonderful, wonderful news. Let's just say that you have a vector function, and f, g, and h are all differentiable. That means you can take derivatives of them. The vector r prime, or also known as dr dt, would just be the derivative of f for your I, plus the derivative of g times your j component, plus the derivative of h times your k vector there. So what you're seeing is you're just taking your derivatives of each component step by step. But of course, we really need to do more than just mechanically take these derivatives. We'd like to begin to really wrestle with what does this really mean? And that's right in here. The geometric significance that r prime represents a tangent vector to the curve at point P defined at t. That's really what we're seeing. And the tangent line to the curve at that point is defined to be a line through P parallel to that derivative vector. So let's just say that we have in this picture off to the side here, just very, very, very importantly, want to point out that you could start with vector r right here. Let's say that's r of 1. And you could say, well, here's your point, and that point we could call P. So, point P is graphed by this vector at t equals 1. Well, if we took r prime of 1, that would be this tangent vector. And very, very importantly, I want to put a star right here. It's very critical to point out and to note that r of t and r prime of t don't necessarily make a right angle. Later in this lesson, we're going to talk about a theorem where we can have that happen under very special conditions. And I think it's very easy for kids to look at a later theorem and think, oh, the derivative r prime must always be orthogonal or make a right angle with the original vector. Definitely you can see in this case that's not true. What you are seeing is that r prime of 1 is really showing how our vector function is changing, how the motion is changing, so to speak. Here we have r of 1. R prime of 1 shows this little arrow. This could be, as we get into physics applications, the direction of motion. But let's just say that we were to say what's happening a moment later. Well, a moment later, here I've just drawn a blue arrow. We would expect a point to come over here. So that derivative, r prime, really is giving us a great idea about the motion of the curve and, giving you a head-to-tail situation, almost like you could add, like, this would be like vector A and vector B to get this new blue vector that I just saw. That would be a great estimate as to what a point on a curve might look like just a little bit later as t grows. So that's super important for you to have that fundamental understanding. The unit tangent vector. Well, a tangent vector, r prime, it doesn't have to have a length of 1. It could have a length of all different types of lengths. But if we'd like for it to have a length of 1, we'll divide by the length of that vector itself. Remember, that's what we did so much in chapter 12. So here's example 1a. We'd like to take the derivative and then find a unit vector where t equals 0. So tell you what, I like to do this too. I know that this might look to be a little bit different. This is component form rather than IJK form, but that's definitely going to be okay. So we have this equivalent vector r written out this way. I really enjoy writing it this way in regards to writing it a little bit more of a shorthand version. So let's go ahead and take our derivative. As we do that, r prime, well, the beautiful thing is we're just going to take our derivative of our first component. That's going to be a 3t squared. The derivative in the middle, we're going to need the product rule. That's going to be a t times e to the negative t, but the derivative of e to the negative t is a negative 1, so that negative is just going to come out in front from that chain rule. And so we'll say plus, then we'll take the derivative of u, which is just a 1 times e to the negative t. Then as we take our derivative of sine of t, well, that's going to be the cosine of t, but we need the chain rule again, derivative of the inside, that's a 2. And there you have it, guys. That's going to be your derivative of your r prime vector. And very nicely, you could write it with IJK form or this component form. But then they're asking us, find the unit vector where t equals 0. Well, for b, let's the unit vector r prime, or how about t, capital T, just like this. Whenever we write capital T like this, that's the unit tangent vector. That's what we should have said. Find the unit tangent vector. One other thing, notice right here, T is bold-faced. You'll see that written in textbooks quite frequently. But my goodness, as we're writing this out, we don't have the option of darkening that in, really. So we'll just put an arrow above it. But when you see something in bold, that's equivalent to saying T with an arrow up on top. Very important to keep seeing that. So look, we're going to be plugging in 0. And if we did that, well, plug in a 0 here. Well, 3 times 0 squared. Well, that's going to be a 0. 0 times your e to a power, that's gone. E to the 0 power is a 1. A cosine of 0 is a 1. And 1 times 2 is a 2. And then, of course, we could say, well, what is the length of that vector? Obviously, right now, this would not have a length of 1. That's 0 squared plus 1 squared plus 2 squared. Well, that's 0 plus 1 plus 4. That's a 5 inside, and we've got radical 5. So when we're finding the unit tangent vector t, we could take this component, 0, 1, 2, and say, you know what, we're going to divide by that length of radical 5. And what are we left with? Well, 0 divided by radical 5 is just a 0. Here we get 1 over radical 5. Then we get 2 over radical 5 right here. And we are done. So for our next part, for example 2, as we're looking here, we've got a curve, and they want us to find the derivative. They also want us to sketch the position vector and the tangent vector. And, finding the derivative, I hope, isn't really all that difficult. We could do that very, very quickly. And again, if we just had r itself, we could write that in components. That's radical t, or t to the 1/2. Here's your t minus 2 minus t times our e to the negative t right there. And then we'll have for our z component, we don't even have a z component. Look at that. That's nice. So as we take our derivative, what's the derivative of radical t? Well, that's t to the 1/2. That's going to be 1/2 t to the negative 1/2, or 1 over 2 times radical t. For our y component, we're going to have to use the product rule. We'll have 2 minus t multiplied to the derivative of e to the negative t. Well, that's 2 minus t times e to the negative t, but the derivative of that inside that negative t, that's a negative 1. Then we'll take our derivative of the first part here, that's the derivative of u. Derivative of 2 minus t, well, that's negative 1. And that's negative 1 times e to the negative t. So there is your derivative. And we're interested in finding out what's happening at 1. Now, I've already graphed this to save time. And we're going to talk about what's happening. To find out what's happening at 1, you could plug the 1 in right in here. And it's only going to take you a moment to see that that's going to be the vector 1. And 2 minus 1 right here is a 1. Here's e to the negative 1. That's 1 over e. And then if we took our r prime, we just found that a moment ago. We'll plug in a 1 right in here. This is going to be 1 over 2. And then as we clean all this up right in here, well, wow, let's see what's happening. This might be just a little bit more work. 2 minus 1 is a 1, so we'd have a negative e to the negative 1. Here's plus a negative e, or negative 1 e to the negative 1. You can see it's negative 2 e to the negative 1, but that's really just negative 2 over e. And right there you found your r of 1 and your r prime of 1. But you can think, what in the world are we really being asked to do graphing? Well, graphing, guys, this sure is reminiscent of parametrics. And I'd like to really quickly review something with you. You could go to parametric mode on your 84 even and select a function. You could go to your y equals, and now you can see it's parametrically written down. Your x1 would be radical t. y1 would be 2 minus t times e to the negative t. And graphing, well, you could adjust and change your window a little bit. My window, I decided to go between negative 4 and 4, just to have some space. You can see t min and t max usually goes out to 0 and 2 pi. And, when you graph that, you're going to get a curve that looks something like this. And you can trace, and you can see actually it looks like it's getting closer and closer to that x-axis. It crosses the x-axis, but it sure is getting pretty close. It looks like it bounces back, starts getting closer to 0. And you could see it a little bit more clearly if you had a better window. But you can see this is more or less what I've just graphed right in here. R of 1, well, if I gave you 1 and comma 1 over e, that's pretty close. If e is pretty close to, about 2.718, e is pretty close to 3 then. So we've done that a lot in the past. It's kind of like saying it's 1 over 3. So you'd say go 1 to the right and just go up 1/3. If this is a 1, if we are going